Hi guys, so this is going to be a quick video just showing you another charge configuration called the electric dipole, which is sort of a good one to have in our repertoire of charge configurations and good to know about its behavior. So far, we've talked about the point charge and the electric field for that goes like 1 over r squared. We talked about the line of charge. Um, where the electric field for that goes like 1 over r when provided this thing gets, really long. We talked about if you have a big sheet of charge, in that situation, if it gets very large, then when you're close to it, the electric field is actually does not depend on the distance. It becomes a constant. When this gets, sufficiently big. And the configuration that I want to add to the mix today is the dipole. So unlike the ones that we've talked about so far, where it's just charge, arranged, this is two charges, one positive and one negative. So imagine on the x-axis we have positive and negative charge kind of arranged around the y-axis. And we're going to look at a point that's just on the y-axis some distance away. And we want to know, what the electric field is doing there. And these charges are separated by a distance d. We'll call this, let me denote it over here, this height above y. So to get started, let's just try and draw where the electric field contributions from each charge would be pointing. So remember, it's going to point away from the positive charge, so there would be at this location an electric field that would be pointing something like that. We could call that one E, from the plus charge. There would also be an electric field contribution from our negative charge that would be pointing along that line, toward it. And those contributions would be the same magnitude because they're the same distance if we're on the, on the bisector. But one is, for one of them, the y contribution is pointing down, and for the other, the y contribution is pointing up. So the y contributions are going to equal 0. They're going to cancel. And so really what we're going to be interested in is the x contribution. So notice for that, both of them are pointing in the same direction. So the x pieces do not cancel. So let's figure out how large that electric field would be at that position, and then we can figure out the components so we can add them together. So to find how big it would be, we need to know how far away it is in terms of this height y and the separation distance d. So one thing that would be useful is we can state r in terms of d and y. That'll just be square root of d over 2 squared plus y squared. So then when we go to find, the magnitude here, at that location, look just like Coulomb's law, kq over r squared. Where now our r will be this y squared plus d over 2 quantity squared. And that's the total from either contribution, just how big it would be. We're going to need just the contribution that is in the x direction. So we can draw this in different ways, but I think it's perhaps easiest to see this angle here. Recognize that would be the same angle there. So if that's the angle that we're working with, we would want the sine contribution of that would give us the x piece. So in other words, the total electric field at that point is going to look like the magnitude times sine theta. And actually, there'll be a factor of 2 because there's a contribution from each charge. Remember, they're pointing in the same direction. So one other thing that we can do is we can state this sine theta in terms of r and d, the geometry. So sine theta in this picture would be d over 2 over r. And we have r right here. So we can put those ingredients together. So we'd have 2 times kq over y squared plus that times sine theta. So we'll pick up a d over 2 times another factor of this. And we could, of course, simplify this. We'll combine these denominators, and we can cancel out this 2. And we end up with this. kq d over y squared 2 squared. This will be to the 3/2. And, you know, a couple things to note. Sometimes you can denote this as the dipole moment, sort of its own thing, where you have, you know, it's given by the magnitude of the charge times the vector, you know, be this like that. And the thing that I want you to recognize about that is that's constant, right? You're not changing the distance between the charges. But if we look at, if you consider when y gets very large compared to the separation distance, d, then look, if you look at the denominator, you can see that that's going to be dominated by the y part. And so when that happens, this E total, let me draw it a little bit bigger, becomes approximately kqd. It's going to be y squared to the 3/2, so this would be over y cubed. So this is kind of the thing that I wanted to point out, is just that for the dipole, when you're far away from the dipole, the behavior looks like, you know, so this choice of y was arbitrary. That's just in our picture. Generally, when we're talking about distance away, you know, r, this goes like r, 1 over r cubed, which is kind of interesting. So the other thing that I would like to draw your attention to is what what this looks like. It's a little bit more difficult to visualize the electric field for the dipole, but just, if you have, uh, you're going to have electric field lines that go from positive to negative. My powers to draw this are going to be pretty bad, but you kind of get the idea. It's going to look sort of like this. There would be lines that would come in to the negative charge and out of the positive charge. So I would encourage you to look in your, that's a little lopsided, look in your text for a prettier drawing of what this thing looks like. But that gives you kind of a rough idea. It's definitely a more complicated configuration than the electric field due to, like a line of charge or a sheet of charge or, a point. So this would just be a slice like through the line that's connecting them. You can imagine this thing would be symmetrical about the line from between the two charges. So, but hopefully this gives you a flavor for this dipole. It appears in some problems, and I think it's a good thing for you to be aware of, and how be aware of how it behaves as well.